Hi, my name is Max Elliott, and I'm going to talk to you today about a recent project that we did looking at the test-retest reliability of common Task-fMRI measures. I am at Duke University, and I work with Ahmad Hariri, Avshalom Caspi, and Terry Moffat. All right, so overall, fMRI has been a really successful tool at detecting robust group effects. As many of you all are familiar, you can see here that one of the first fMRI tasks that we've ever performed was a visual stimulation task. This was published in Science and showed that we can get these nice colorful blobs on the visual cortex when you see a visual image in front of you. We've advanced this methodology to many different types of tasks. These include when you look at faces compared to objects, you can see activation in the fusiform face area. When you look at when you get incentives, you can see activation in the striatum. You get this really nice left lateralized language network when you do a language task. And a task near and dear to the heart of my lab, this is when you look at threatening images, you see activation in the amygdala. So to dive into a specific example, you can see here that when you compare activation in the amygdala, when you compare activation during facial images, particularly like fearful faces like those shown here, to activation when people look at dots or shapes, you get reliable and robust activation in the amygdala. Importantly, this is a within subjects contrast. So what this means is that you bring a bunch of people into your fMRI scanner, one at a time, you scan each of them, and you compare activation during faces to activation during shapes. So this is a within subject contrast because you're comparing activation to faces to activation to shapes. This robust within subject effect has been replicated over and over again. So as you can see here, there's 4 different studies that we've in our own lab investigated, and you can see in each case you get robust activation of the amygdala. This is also true if you do test-retest studies. You bring in the same subjects twice. In the case on the left, we had 20 subjects who were age 45. In the right, we had 45 participants, young, healthy adult participants. And in each case, you bring the same people back. You robustly and reliably get this signal in the amygdala. However, most of us aren't just interested in task contrast. A lot of us want to understand psychopathology or mental illness, and we want to understand if there's more activation in the amygdala to fearful faces or threatening images. Maybe people who have more activation when they look at those fearful faces have more of a likelihood of developing anxiety or depression. And our lab has done many of these types of individual differences studies where we try to compare whether subjects who have more activation in the amygdala had psychopathology. So for example, in this paper that was published in Neuron in 2015, we found that those who had higher amygdala reactivity, who were exposed to life stress, were more likely to develop depression later in life. However, until recently, this jump from this group within subject activation of the amygdala to this between subject effect, where we want to understand individual differences in amygdala activation, hasn't been investigated fully. So particularly, there's the between subjects effect, when you start to look at individual differences, relies on quite a different framework than the within subjects robustness of the effect. So to illustrate this, I'm going to look into a quick example based on data that I completely made up. So here you'll see that we have 3 subjects. I'm going to show you that their amygdala activity is greater than 0 because it's on the right here. So we have the green subject, the blue subject, the purple subject. All of them have activation to faces that are greater than activation to shapes. And I'm illustrating that with these bars here. So if we plot, we run a group study and we plot a bunch of subjects down here. And on average, you can see that they vary in their amygdala activation, but it's all greater than 0. So if we run a statistical test and we compare this group mean to 0, we can reject the null hypothesis and say, hey, we have a significant group effect. This is a robust activation of the amygdala with this task. Then we want to map this out to psychopathology. So I bring down all of their activation measures, and I look at some measure like, let's say, depression. And we can see that there's significant correlation. Yay, there's effect where maybe activation in the amygdala could be some type of biomarker for depression. This is a very commonly used approach that we've seen in the literature many times. However, we're good scientists and we want to actually test to make sure that this effect is replicable. I want to make sure that this wasn't just a fluke of my study and that I could get this result again if I repeated my study. So here I have amygdala reactivity at time 2. And again, I have these same subjects. I brought them back to repeat this study. This time, we can see that their bars moved around a little bit. They have slightly different amygdala reactivity values. But the group level effect is still there. There's a significant robust within subjects group effect. The amygdala is activated more to faces than to shapes. However, this time there's no correlation between depression and the amygdala activation at time 2. And I just want to convince you that this is a possibility. This could happen. We could have robust group level within subject activation without reliable or repeatable between subjects correlations with other variables. And the reason that this can happen is that if I take the brain activation at time 1 and the brain activation at time 2, this is a test-retest reliability study. And in this case, because the subjects moved around in their activation, their amygdala reactivity, there was a very low test-retest reliability, which here I'm going to measure using the ICC. And this is a common method to measure reliability. It's very similar to just a Pearson correlation between time 1 brain activation and time 2. So in this case, the reliability of individual differences was very, very low. ICC ranges from 0 to 1, and we had an ICC that was less than 0.1. So you can have unreliable between subjects effects despite very robust within subjects effects. This possibility led our group to want to investigate, well, how reliable, if we look at test-retest studies, how reliable are commonly used Task-fMRI measures that we use? Task-fMRI is widely used to do individual differences studies. So we wanted to know, how are we doing as a whole? How reliable are these Task-fMRI studies in the way that they're in one way that they're commonly used, which is to extract activation from an ROI. So we did a big Google Scholar search, and we found over 1,000 papers in our original search. We screened these, and ultimately we ended up with 56 studies that reported test-retest reliability estimates for task activation in an ROI. We fit a random effects multi-level meta-analysis to these 56 studies. And importantly, in doing this meta-analysis, we found 13 studies that we are going to leave out of our main meta-analysis because they thresholded on ICC measures. And this is an approach that is kind of very similar to double dipping, if you're familiar with that term. But what this did was it biased the reliability or the ICC higher because they threw out low ICC values that were unreliable. So what did we find? Here we have every single study as a row in this big forest plot. And I color-coded this figure so that each color corresponds to different kind of levels of reliability, red being poor, orange being moderate, yellow being good, and green being excellent. And as you can see here, after fitting this running this big meta-analysis, the ICC on average across every single test-retest study we could find was 0.397. And this is right on the edge in the poor range. So this is not a very good estimate of reliability overall. And these studies that were thresholded, so the studies that threw out the low ICC values, had reliability estimates or ICCs of 0.7. So you can see that this inflation of the ICC occurred, as we expected. However, there's a ton of studies here, and there's lots of different tasks. These are not all the same tasks. And a lot of these test-retest studies came from 10, 15, 20 years ago. So there's a lot of heterogeneity in these estimates. While it represents a kind of average of all test-retest studies, it doesn't necessarily represent the reliability of individual studies or tasks that are commonly used today, or modern fMRI scanners that have improved dramatically in the last 20 years. So we followed up this study by running two new test-retest analyses in data sets that we had access to. The first one was the Dunedin study. In this study, we had 20 adults who were age 45. There were 79 days on average between test and retest interval. And we looked at 4 fMRI tasks that are very commonly used in the fMRI literature to look at individual differences. And because this was our study, we wanted to also test open access data sets that we had access to. So here we looked at the Human Connectome project. This project represents state-of-the-art technology, scanning technology, and is really a gold standard for a lot of the field. Here, there's 45 healthy adults, aged 25 to 35 years old, who were scanned twice, and on average, there was 140 days between test-retests. Here, there were 7 fMRI tasks, and importantly, 3 of these were very similar to Dunedin. All of these tasks were very similar, so we're able to test the replicability of our reliability estimates. In each of these tasks, we picked an ROI that was the most commonly used ROI that people are interested in to look at activation, particularly when you're looking at individual differences. For example, for the emotion task, which was those faces tasks that we showed earlier, we used the amygdala. So I'm going to orient you to our results, which will all occur in this type of plot. So what we did was we took we calculated the ICCs for task activation in each of the ROIs from all of the tasks. And for the ROI that is of interest in that study, we circle this in black here. You can see the amygdala is circled in black, indicating that it's the amygdala of interest, because we wanted to test whether the task or the ROI of interest was more reliable than ROIs that weren't necessarily investigated or targeted by that task. So as you can see here, the reliability is about 0.3, which is, again, not a very good estimate of, not a very good reliability coefficient for the emotion task. This pattern was consistent across all 4 tasks in the Dunedin study. There's only one task that was above the moderate threshold, and that was the reward task. But in general, a lot of these ROIs were pretty low, had ICCs that were pretty low. Well, we were interested in whether this was something about fMRI in general, or if this is something, whether this expanded to other areas of MRI. And we found that actually cortical thickness and surface area were very reliable estimates. So this was something about task fMRI, not brain imaging generally. But we wanted to repeat this study, and we found very similar results again in the Human Connectome project. Overall, there were not very reliable estimates, and most of the estimates were in the poor range. But again, as you can see here, cortical thickness and surface area had very reliable estimates. So the structural brain measures were very, could detect individual differences very reliably. So across these 2 studies, what are our main conclusions? First of all, robust does not equal reliable. The tasks I showed you all elicited very robust within subjects differences, but did not have very reliable between subjects differences. Importantly, from the meta-analysis and our task fMRI analysis, many fMRI tasks probably have insufficient reliability for individual differences research, because they will give you underpowered, unreplicable, non-replicable associations that we probably want to avoid, and we want to make sure that we're getting really good individual differences measures for our studies. Importantly, we can't generalize to all fMRI tasks. We investigated a small subset of all the possible fMRI tests there are. For future investigation into specific fMRI tasks is definitely warranted. We think that major changes in practices is needed so that we can build a cumulative science in task fMRI. Currently, a lot of individual differences studies investigate these tasks that we're showing you right now. And we want to be careful to make sure that we have a cumulative science that's built on reliable associations. And right now, this current state of many of the test-retest reliability estimates here aren't high enough for that. What are our recommendations to improve reliability? First off, studies of individual differences should report reliability. We did a big meta-analysis, but we think that each individual study that investigates some between subjects correlational association between fMRI and a behavioral measure or psychopathology or anything of that nature should give us the test-retest reliability so that we know how reliable those estimates will be. And it will inform power calculations as well. Next, we emphasize the development of reliable tasks for individual differences studies. So many of the tasks I showed you came from cognitive neuroscience. This literature has given us lots of interesting information about how the average human brain works, but these tasks weren't designed to be reliable from the beginning. They were designed to be robust. They were designed to elicit activation. So we think that a lot can be done just by focusing on reliability from the beginning. In order to do that, we think embracing ecological validity over experimental control could make a lot of headway there. So actually embracing the variety and in the variety of stimuli in the world around us. So for example, like movie data is much more similar to the world around us than simple fMRI tasks where you look at faces. And importantly, there are ways to measure fMRI beyond task activation. So we could look at whole brain signatures instead of ROIs. We can look at structural measures. They're very reliable. Functional connectivity, especially with longer scan lengths, has been found to be reliable. And there's initial evidence saying that multivariate and prediction analyses actually give more reliable estimates because they filter out noise in the cross-validation. I just want to thank all my co-authors. This paper is out as a preprint if anyone wants to read more about this, and it is accepted and will soon be published in Psychological Science. Thank you.